Solar power.
Hello, my name is Jack Opgenorth, and my teammates are Noah Batiuk, Sarah Hildt, and Jadon Latta. And our client for this project was the Northern Alberta Radio Club, aka NARC. So the main goal for our project was to design and construct a scalable solar power generation and monitoring system that could be deployed to different sites with a variety of different power requirements. And chief expectations to accomplish this were to, number one, design a system that could generate and store solar power as backup for the NARC radio sites. Two, to provide a remote monitoring system via a web page and also radio that could display various metrics pertaining to the system to NARC members. And three, to design the system to be easily deployable and scalable to satisfy a variety of different power requirements at different sites.
All right, this is where our system begins, our solar panel array. Right now we've got two panels giving us a 24-volt system. In the final product, this would be replaced with four 100-watt solar panels in an array to provide the 24 volts still, as that matches the rest of our system. But these are just test panels we are using because we had them, and they are enough to test the system and make sure everything is working properly. You can see the cable here is running along. This will connect to the rest of the system and then be supplied to the batteries, as we'll show right now. Here is where these solar panels connect to the rest of our system. The first place they go from here is into a fuse and then into this chip, which is a current sensor. You can see the panel comes into here. This reads the current going through the cables right now and reports it to the rest of our system for measurement. After this, it will follow along this cable into our solar charge controller. This is here to prevent overcharging of the batteries and prevent voltage spikes from the solar panels from frying the batteries from overcharging. It'll see here, it has multiple different settings. We can check the amperage going from panels to batteries, the panel voltage, the battery state of charge, and the battery voltage, alongside some other functions if we attached a load to this charge controller, which is not part of our system. Here, it leaves the charge controller following this cable, leading into this battery box here, which is a 24-volt battery system that will eventually be connected to the inverter and the rest of the system once it's installed on site.
So here we have what is basically the monitoring system for our device. So really that starts right here with the current sensor, which is detecting the current, as has already been mentioned, and then that just goes straight to an analog to digital converter, which is shown right here because it's an analog signal. We need to convert it before we can actually do anything. And then that analog signal comes out as digital right here, which goes straight to the Pi, where it is then sort of processed and displayed on our very fancy looking website. Besides the current sensor, we also have our temperature sensor, which, because our temperature sensor is actually digital, so it doesn't need to go to the converter, it just goes basically on here and then straight to one of the input pins on the Pi, where it is then sort of detected, processed, and displayed to look nice on our website with everything else. And yeah, that's basically our monitoring system.
So part of our system is to send radio notifications, and that's done via a radio. So if we look over here, we can see that we used an RS-232 cable to complete the communication. So there are three main pins that we use with that. We use the ground pin, we use a push-to-talk pin, and we use the data transmit pin. And so for the push-to-talk, that circuit was described previously in the poster, and it's all inside of this plug here. And then if we come over, we follow the cable to the Pi, and we can see that the push-to-talk pin is plugged into one of our GPIOs. And so when a notification is to be sent, the GPIO pin will go high, which produces 3-volt output, and that is just enough to enable the transmission to begin. To actually send data, we just use the output from the Pi itself. So we can see here we have a sound card and a headphone jack that leads us all the way to the data output pin. And so once the transmission is enabled, the output is just sent via the Pi all the way to this pin, and once it's complete, the transmit ends. And we can see that in the following video.
B6GRS, ambient temperature of 21.9 degrees. CPU temperature is 55 degrees. Current in the panel of 0.26 amps.
Website time. The backend of our web server is built in Django, which is primarily made in Python. As you can see here, this is what our website looks like. And right now it's displaying metrics that are being taken in from the various sensors connected to the Raspberry Pi. Right now our website is hosted on localhost, which is just a local host, but later on it'll be hosted on NARC's official DNS. So all of these values here have various thresholds in a configuration file. Things like the refresh rate, currently it's set to 5 seconds. So as you can see, these values should be updating every 5 seconds. As well, we have various thresholds. So if a temperature or a current value exceeds an allowable threshold set in the configuration file, it'll send an email notification out to every recipient also specified in the file. So anyone who's invested in the current status of the NARC site will have ready access 24/7 to all of the various details. As well, all of the current and temperature values will be broadcasted over radio frequencies every 30 minutes.
There were 4 main components to our project. The first was our power generation and storage system. Although the number of watts generated was smaller than initially planned, the system was still able to successfully generate solar power and store that power in a battery bank. Additionally, the system is designed for a much higher current output, so our sponsor can easily swap the older panels in for a newer model and acquire the recommended output. For our monitoring system, our system was able to successfully monitor the current output from the solar panels, as well as the room temperature and the temperature of the Pi CPU. Metrics collected are currently displayed on a local web page. In order to view the web page remotely, users could simply host that web page on the internet using NARC's DNS. Our system was portable and extendable. The system was designed to be modular, meaning that 2 of our designs could simply be added together for increased generation and storage. The client has been provided with instructions on module combination and charge controller resizing. Additionally, while our prototype includes only a single temperature and current sensor, a configuration file exists such that users can specify when new sensors are added to the system. As such, additions can be made by easily adding a single parameter to the configuration file. Finally, we have a remote notification system. Users may wish to be notified of certain conditions in the system, such as excessive current or temperature extremes. As such, they may choose to enable notifications. Our system will send an email for every 30 minutes the system is experiencing an undesirable condition. Additionally, the system will send regular updates via radio to those who wish to know system status. The system thresholds and notification intervals can be easily altered using the configuration file.
What didn't work with our project? So the main thing that didn't work in our project was us trying to make a sort of more permanent and also self-contained distribution system for power to our various components. So our idea for this was basically to create a very simple PCB, that is printed circuit board, that basically we would just plug our batteries in our system into, and then this would be able to just provide different power to our various components, kind of chief among them being the Raspberry Pi. But the main thing that didn't really work out here was the fact that our group members didn't really have a whole lot of PCB design experience, which led to the design process kind of taking a little longer than we expected to. And also, various aspects of the PCB design were a little bit subpar, kind of chief among them being traces were probably a bit smaller than they needed to be. And also, and probably the most important part, was clearance between tracks was not enough, which led to various problems. Kind of the second thing that didn't work out, which was very related to that first point, was the DC to DC converter, which we were using for our project. Basically, the point of this converter was that it was supposed to take the 24 volts from our batteries and then convert that down to 5 volts, which could then be used for all our various components. Unfortunately, this converter didn't really end up working out for kind of 2 main reasons. The first was that the converter did not really have adequate protection, which kind of led to it seemed to be very prone to very high voltages happening suddenly when we would plug it into our system, which led to kind of it being damaged or destroyed. And we kind of ended up going through a few converters that way, which was unfortunate. And then also kind of second point of why the converter didn't really work out was we were not really as careful as we probably should have been when testing the converter, particularly when we were plugging it into our system. And the 2 other points, so climate control was another aspect of our system that didn't really work out as planned. This was basically a goal that we had initially when talking to our client to be able to control the temperature of our system so it could survive in a variety of climates. Unfortunately, we kind of just ended up having to prioritize other more essential elements of our system to make sure we had a good project, or good prototype, I should say. And then last but not least, one thing that we wish we could have done more on was a more detailed website interface and customizability. So currently we do have a sort of limited interface for our website to display our various metrics and whatnot, and also some basic customizability for adding and removing various metrics. But ideally, given more time, we would have a much more sort of fancy interface for displaying our metrics, so like various ways like plots or whatnot, and then also better ways to customize exactly what is being displayed and how it's being displayed.
Overall, our project was quite successful, but there are a few key pieces of future work that we have identified and outlined for if the project was to have a little bit more time or if another team were to take over after. The first and likely most important one of these future works is a more permanent and compact package for our sensors, preferably a PCB that is designed and printed. This would include all of our sensors, converters, and the server chip, which right now is the Raspberry Pi, and would make it so that we have a nice standalone chip that is easier to use and smaller, and generally is going to improve the performance of the system. Another possible improvement, and another very important improvement, would be a more detailed user interface for the website. This could have some more customizability with modules for different sorts of visualizations of data, as well as just generally being a little bit more user-friendly and having some graphics, maybe a logo for NARC, etc. The third future work piece is proper field testing with better solar panels. For testing and design, we were just using cheaper solar panels that NARC had on hand, and if this system were to have a little bit more time to test, it would be nice to get some newer, higher quality solar panels to make sure that the charging is working as intended. As far as the research and design has gone so far, it should work perfectly, just plug and play. The final piece of future work that we think would be very important would be adding a circuit breaker to the system for improved system safety. There's already fuses existing in the system, but adding a circuit breaker would be a straightforward and effective improvement to increase the redundancy of our safety systems, which is always important and useful.
Over the course of this semester, we have successfully designed and constructed a scalable solar power generation and monitoring system prototype for the Northern Alberta Radio Club. This system contains a full set of sensors to monitor current from the solar panels, indoor, outdoor, and CPU temperature. The system can also broadcast these values across online, email, and radio link mediums. Our main components were solar panels, a solar controller, an ADC, temperature and current sensors, and a Raspberry Pi to host the managing website. Overall, the project was a successful prototype, but will require future development to transform it into a complete product. Thank you so much for watching our presentation.